Hello and welcome to Sean White's Solar and Energy Storage Podcast. The title of this podcast is Energy Storage, PV, and the NEC Workshop, which is a workshop that I did on August 6, 2021 at the ASES conference at the University of Colorado Boulder, and it was a lot of fun. If you're listening to a pure audio version of this podcast and you want to see the presentation itself, you can go to my YouTube channel, which you could get links to at solarsean.com. Also, you can see a lot of this material at HeatSpring. And by the way, if you like that last podcast that was the Solar PV Intensive Workshop at the ASES conference, we just registered that for NABCEP credit at HeatSpring. So if you need a couple of hours of credit for NABCEP continuing education, you can go to heatspring.com/SEAN. You can find my classes. And a little ways down, when you see the free classes, look for the class called Introduction to Solar PV Design, Installation, and Code. And there's a few more things in there besides the ASES Intensive Workshop, but check it out. It's not too often that you get free NABCEP Continuing Education credits. Also works for NABCEP Prerequisites. Kind of works for about NABCEP everything. Okay, now what I'm going to do is I'm going to read the description of this workshop that once again is titled Energy Storage, PV, and the NEC Workshop. This workshop will be jam-packed with NEC insight and interpretation. Sean White teaches PV courses around the world and has authored many technical PV books. Solar Photovoltaic Basics, 2nd edition, Energy Storage Basics, Solar PV Engineering and Installation, 2nd edition, Solar PV Technical Sales, and last but not least, PV and the NEC 2nd edition, and that was co-authored with Bill Brooks. Sean will fill you up with as much information as possible in the time given while entertaining you. This year, Sean will focus more on energy storage systems, that's ESS, than he has in the past. Did you know that the NEC allows us to backfeed your house with electric vehicles, and that it is just the EV manufacturers holding us back? Be ready for when EV manufacturers let us do what they already should have. That's backfeeding the grid with your car, which I bet happens in the next 5 years. This course will count for NABCEP continuing education requirements in every category and will also count for prerequisites for NABCEP certification. And this course will also include a $200 discount for Sean's advanced online PV classes. And this course also includes a printable color digital certificate included, along with the PDF files of the presentation. Your instructor is US-based, teaches classes internationally, and his resume can be seen at MaximumPowerPointTraining.com. Okay, here we go to Boulder, Colorado, August 6, 2021. For a copy of this presentation after we're done, and for a certificate of completion, just send me an email. So there's my email. There's my website, SeanWhiteSolar@gmail.com, SolarSean.com, and we can get that to you. And I also do have like some different books if anybody's interested that's here right now. They're $30 each, or you can get them. They're about the same price there on Amazon. This one is PV and the NEC. That's the 2020 version of the NEC, and that's kind of what we're going to talk about. But we're always going to compare and contrast 2020 and 2017. There's a lot mostly similar, 99% the same. And people a lot of times focus on what has changed. That's just the rules for installing electrical systems in the United States and in other places. This is the 2020 NEC. And so what we have here is a yellow dwarf star, and it's actually a white star, but some reason they call it yellow. Probably because after that sun goes through enough atmosphere at sunrise and sunset, it starts looking more yellow. But when you see a solar eclipse, and the sun gets blocked by the moon, except for like this little piece. They call that the diamond ring effect. It's the most religious experience I've had almost seeing that. And it's very white. It's just like this bright white star that's up there. And our star is a younger one. It's only 4.3 billion years old. The universe is over 13 billion years old. We've got another 7 billion to go before we have to figure out the different solutions, or just, adapt our genetic code. 2017 NEC also was very solar oriented. It had solar on the cover. So we had PV on the cover of the NEC. And the first time they ever came up with Article 690 photovoltaic systems was in 1984. That's George Orwell's version of the National Electrical Code. And it was a very small NEC. It was like almost a pocketbook. So the NECs got bigger and bigger. This class also counts towards NABCEP credit if anybody needs that. And one thing I did is I did an NEC class one time, and I started off and I pretended I was going to do the 1897 version of the NEC. And I was like, oh, NABCEP didn't say what version, but it's mostly different, but it's kind of interesting. So I have a little presentation on that. Sometimes I joke around with and use. This is the book PV and the NEC. And I wrote this book with my friend. We own a sailboat together. His name's Bill Brooks. A lot of you probably have heard of who he is. He's the guy that gets really active in writing the NEC. And when I get a copy of the NEC, I get it from Bill in a Word document. That's the first time I'll see it. So probably next year, just about a year from now, I'll get it from Bill and it'll be a Word document on his computer. And it's mostly right. There's still a couple of things that might change. Where do you get the NEC? The one big complaint that I have about the 2020 NEC is the NFPA. That's people that publish it. And they are supposed to be a nonprofit, but I'm sure they pay themselves well. And they didn't make the PDF version, and probably because they're afraid people are going to pirate it or something. And so now it's very difficult to log in for the digital version. And I'm like offline a lot of time, and I have to log in 4 or 5 times a day because it keeps signing me out. And I go to this page and go to this page and all that. It takes about twice as long now to do stuff when you don't have the PDF version. Like, not too happy about that. Sometimes I still even just use the 2017 NEC when I know it's going to be the same because it's so much easier to navigate. So if you have any push or pull or lobbying, just tell them that they need to change it back. I made a YouTube video about that too, of how awful it is that we can't use the PDF. It's the rules that we have to follow. It should be easy to access. 2017 NEC, you can get a PDF copy free on the internet now, and it's from archive.org. And if you just Google Texas Tool, I think it's Tool is the name of a city, they give it to you for free. So that's interesting. So just some facts and data to get us interested in as we're starting out here is I like looking at the cumulative watts per capita for these different places. And we could see Hawaii has 467 watts per person. So that's pretty good. And I think these numbers are for 2019. So I'm sure it's probably over 500 watts per person now because this industry grows fast. And then the next is California, 228 watts per person. That goes to show you how full the grid is. And that goes to show you also places where you might be looking to do energy storage, because as we get the grid more and more saturated with solar energy that peaks at noon, then we're going to need to be able to shift that noontime energy to the evenings. And that's what energy storage is. And in Hawaii, you pretty much have to have energy storage most of the time because you can't export. I mean, there are some cases where if like you had a big factory and a small PV system, you'd never export anyway, because even your peak wouldn't be as much as you're using. So these are all the best states for solar. Let's pick on the worst state for solar, North Dakota. Anybody from North Dakota? Nope. See, because nobody from North Dakota is here because the solar industry is so bad, you get penalized. They need to get it together up there in North Dakota. There's probably just like 41 houses. Whoa. I got it from the SEIA website. I got this off the national ranking 2019, but I did get off the SEIA website just a month ago or something. I'd say worse things, but the AV guys would have to bleep it out. Now we're looking at the National Electrical Code, and there's different ways that it's organized. And so we have chapters 1 through 4, and this is for all installations. This is general stuff. Solar people, energy storage people, everybody has to follow it too. And oh yeah, by the way too, I started off like before previously when I did this presentation for ASES, I started off with PV and then energy storage would be second. So now I've said energy storage first, PV second, to mix it up and have a different focus, because that's the new thing that everybody's so interested in. Chapters 1 through 4, that's all the stuff that you always have to follow for everything. Chapters 5 through 7, that can supplement or modify 1 through 4. And so we have Article 690 is in Chapter 6. And then there's some things that we're going to talk about in Chapter 7, has things that start with a 7. So that would be 705. That's interconnections. That's how to like backfeed the grid, for instance. AC microgrids, DC microgrids are in there too. Standalone systems. Energy storage systems is 706. We'll spend a good part of our time there in Article 706, energy storage systems, when we're going to talk about how that kind of conflicts with Article 480, storage batteries, and why that. We'll get into that. Chapter 8 is kind of different from the rest of the NEC. It's about communication systems, but that also is important because we're doing a lot of communication because we're bringing currents from our electric cars and our solar and our batteries. And there's new ways of doing that where we don't get penalized
like we do with, some of you might know about the 120% rule and how much we can backfeed. We'll get into that a little bit too. Chapter 9 is where there's lots of tables and things. NFPA publishes a lot of stuff. This right here, what we're talking about, is a standard for energy storage systems. You could say like, well, we already have that in the NEC. That's Article 706. The NEC is the widely adopted code that there is in the United States. Out of any building code or anything, it's adopted by all 50 states. The different I codes or the ICC codes, International Code Council codes, they are not adopted by every state. There are some states that adopt the NFPA fire code, and other ones do the International Code Council fire code, the IFC. There's different states do things differently, and no state has ever adopted this new standard for energy storage systems. It's just like, but there might be an insurance company that makes you do it, or something when you do an installation. It's worth reading, but it's a new code. It's not perfect yet, and they've got to work on it some more. And it's just one of these things we'll be seeing in the future. I'm not going to go through all these things, but energy storage is for a lot more things than just storing energy for long periods of time. So everybody thinks of like, oh, I got an off-grid system. I put energy into my battery, and then hours or days later, I take it out and I do something else with it. But with energy storage, the number one thing that people like to use it for is frequency regulation, as far as like what's these megawatts of batteries on the grid in the world. And it's like a wind farm in Australia kicks up. It was the biggest energy storage system in the world. And what happens is when it kicks on and slows down and there's a gust of wind, we can match that with some energy storage to make up for these, huge, giant increases and decreases in power. So we call that frequency regulation and voltage regulation and all these different things that we could do with the electronics associated with the energy storage systems. If I had a 1 megawatt energy storage system inverter, I could do a 2 megawatt change, because I could go from full charging to full discharging. That's a 2 megawatt change. And I'm just telling you that, and those megawatt, that's power. And that's another thing about energy storage systems too, is people think like, oh, it's megawatts or is it megawatt hours? You get kind of confused. And so it's both. The megawatt, and it could be kilowatt too, just megawatts are 1,000 times bigger than kilowatts, is that the megawatt is how much you could do all at once. That's the rate. And people, when they talk about energy storage system capacity, they talk about that, the power. And if you talk about how much that energy storage system would hold, we're talking about the energy. So it's kind of funny. We're saying energy storage, and then we're talking about the capacity, and that's not even energy, that's power. But you can't store power. This is AC coupling. Once again, AC coupling, the easiest way to make that, to get that point across, is with AC coupling, what you do is to charge the battery from PV. So a battery is direct current, PV is direct current, but to charge the battery, you have to convert to AC and then back to DC. And you might want to ask like, well, that sounds stupid. Why would you ever want to waste all that energy doing these conversions? And everything talks the same language when you're doing this AC. So you've got like one brand of this and another brand of that, and this thing breaks, and 10 years later, you got to fix this. If they all are working with like 480 volts AC, for instance, or 240 volts AC for your house, it's easy to just go, oh, I got a different brand. So like over where I live, we have microinverters that we installed 10 years ago, and that's working with the Tesla Powerwall that we just installed this year. And it all works together because it's doing AC coupling. That's some of the reasons why you might want to do AC coupling. And if you have DC coupling, what we have here is the PV, and I could charge the battery all with direct current without converting. So there's less conversion losses, probably have to have everything the same brand, or things have to work together that way. But, less conversion losses is pretty good. And then another thing too is less inverters. I only need one inverter there. So that's a different benefit there. And this is a symbol for a DC to DC converter. So this particular one, we're calling this DC coupling. And this is where utility scale, typically DC coupling, they take a PV inverter, it's not an energy storage system inverter. And then they kind of modify that. And then on the DC side of that PV inverter, they get this battery to go just the right voltage to work with that PV inverter on the DC side. Another thing though, too, is a PV inverter is a one-way thing. You can't really charge the battery from the grid with this too. So another drawback, and they could design it different so that inverter could charge the battery from the grid. This is called reversed DC coupling. We put the DC to DC converter with the PV, and we have an energy storage inverter, and that way we can charge the battery with the grid if we need to. So that's just a different type of DC coupling. Instead of having separate boxes, you just put them all in the same box, and they call that a hybrid inverter. With a hybrid inverter, what we have is we're putting the PV and the battery connected right to the inverter. And that kind of can make things simple. A lot of smaller systems are like that, like Solar Edge does it that way. That's called a hybrid inverter. According to the NEC, though, a hybrid system does not include batteries. It'll say like a hybrid system means it's PV and wind or PV and a generator, but not batteries and not the grid. They exclude the batteries in the grid. So a hybrid inverter is not necessarily hybrid according to the NEC definition, but according to my friend Bill, they're probably taking that out in the 2023 National Electrical Code. Just remove the term hybrid from the NEC. Just like they did in the 2020 NEC, as we're going to see coming up, they removed the word solar panel because solar panel is a group of modules and everybody would just get all confused. And so we got to correctly say solar module means one, rectangular thing. And then solar panel, as you put a few of them together, and that kind of goes way back to the day when solar modules were $1,000 a piece and really small. So they would put them together on the workbench and wire them up before they went and put them up on the roof. Here's just some NEC articles we're going to look at. And these are related to energy storage systems. And we have batteries, storage batteries. And that's kind of like the old timer thing. It's like, Thomas Edison, he's an old timer. And if you want to think of it, like if you're talking Article 480, you're probably talking lead acid batteries or what are similar to NiCads, like these old battery where you add fluids to them and they don't come with an inverter built into them, or they don't have like an electronic off switch. They're not listed to all these new energy storage system terms. And then 706, that's the modern one. And so when they came out with 706 in the 2017 NEC, the intention was to get rid of 480. But then what happened was some people didn't want to get rid of it. And a lot of it probably has to do like also the telecom guys. The telecom guys, they don't need to change their ways. And I don't really blame them, but they have this thing behind a fence. It's not in your garage. It's not like your kids are going to be walking around it. They don't want to have a disconnect or something like that. So it's kind of interesting that for a lot of these lead acid batteries, NiCad batteries, you don't even need a disconnect. Energy storage system 706, we're usually talking like there's no UL 9540 listed energy storage system. That's the listing that we use for these that does not come with an inverter. So it's almost like if you wanted to be really strict at interpreting the code, you can't even have a DC energy storage system, because there's no listed one. That could change, but just nobody's gone to the trouble to list it that way. Another thing too is 690 in the 2014 NEC and earlier was full of battery stuff. And they took a lot of it out and they made energy storage systems, and they took out part of it and they made standalone systems. And so they really separated things out. Here's standalone systems. It's a very short article. It's just about, being off grid. And 712 is DC microgrids. And they might combine that with Article 705 at some point, because 705 has AC microgrids. So that's something that some people are trying to do. And then the rest of the NEC also, you also have to comply with when you're doing anything. You don't just read one chapter and that's how you do it. Here we've got, and this is some of the stuff that I've just already said. Also, too, I have a lot of material here, a lot of slides. So I'm going to have to skip through some of them. I'm going to keep them here, distribute them to everybody so you can have copies of all these slides. 2017 NEC, we made a lot of changes. In Article 690, it's like, if we're doing a PV system with batteries, energy storage, do we use 706 or 480? So in 690, it says an energy storage system connected to PV system shall be installed in accordance with 706. So that directs us away to 480. Another thing, though, is 706 only applies to systems over 1 kilowatt hour. Most energy storage systems are over 1 kilowatt hour. You could maybe make one that's just a little bit less and trick the code, find a loophole or something. Energy storage system, I'll just read the definition. One or more components assembled together capable of storing energy and providing electrical energy into the premises wiring system or an electric power production distribution network. So it's pretty much an inverter even by that definition, because who's got a DC house? It's not going to be that common. It's into the premises wiring system. That's where you're going to distribute to. 480 is in chapter 4, and that just goes back to the days of Thomas Edison. But we do have some interesting things in there. They talk about nominal voltage. So your 12-volt battery in your car, I always like using that for an example. It's not 12 volts. Once in a while, maybe if your battery's dead, it passes through 12. If you're driving down the road, it's over 14 volts because your alternators go in. Airplanes, small airplanes that have a 12-volt battery in them, they call them 14-volt radios. They don't call them 12-volt radios because they're going to be closer to 14 volts when you're flying around. And they want to be more accurate, especially with avionics, because it's not good when your engine dies when you're in the sky. A battery that's just charged and sitting there, like all our cars, it's probably around 12.6 volts. and it's charging it over 14 volts. Lithium ion batteries, the ones that have cobalt in them, like most of the cars, they're about 3.6 volts, we say nominal. They charge them up to 4.2 a lot of times, and that's per cell. So the lead acid batteries are 2 volts per cell nominal. So 6 cells in series in your car. And then you do have something though that they don't have here. It's called lithium ion phosphate. It's another type of a lithium ion battery, but it's 3.2 volts. And I think when we were having these meetings last year online, I mentioned that. And so I think it'll be changed in the code because it's kind of leaving the lithium ion phosphate out. Here's just what I said. It's kind of smaller and it's harder to read, but you can see this when we do the presentation. It's just showing these different ranges of how this works. This one is a nickel metal hydride battery. I used to have one of these in my car. That was from the Generation 1 Prius. And here's just what I was just talking about. And usually like they're saying like the cobalt batteries, cobalt's bad for the environment, by the way, or, it's bad for child labor in the Congo. Half the cobalt comes out of the Congo at least, but it works really good for lithium ion batteries. And so Tesla typically uses lithium NCA. So lithium, nickel, cobalt, aluminum oxide. And then a lot of the other cars, there's some mixing. So Tesla uses the other technologies too. And then the other cars is NMC, lithium, nickel, manganese, cobalt oxide, NMC. Those are the main types that you use in your cars. And then there's lithium iron phosphate, LFP. Lithium iron, F is for ferrous, and that's just because somebody decided that ferrous is iron, some Latin guy probably a million years ago. Now we're diving into energy storage systems. Let's just get to some important stuff here. Nominal voltage. Sometimes you see amp hours, and amp hours is something that if you're working with battery cells or just batteries and stuff. And so you have to take amp hours and multiply it by your volts to get your energy. So amp hours multiplied by times volts is your energy. If you want, you could also divide it by 1,000 to turn it to kilowatt hours, or forget the 1,000 and you turn it to, and it's just watt hours. Amp hours times volts equals watt hours too. That's the calculation to do. These days with energy storage system, you don't even know what the amp hours are, You want to know how much energy that battery has. Residential batteries, a lot of times somewhere around 10 kilowatt hours, it depends. Some people will get plus or minus, not exactly. And you don't cycle them all the way down and you don't cycle them all the way up, or it's not good for the longevity. With lead acid batteries, it's good to keep them top off, but it's not good to let them cycle down more than 50%. With lithium ion batteries, it's usually not good to overcharge it or undercharge it. So not to 100%. I keep my car between 80 and 20 usually. Let's see. So what we have here, this is just where the NEC kind of contradicts itself on the same page. It says a battery storing energy is not an energy storage system. And then it says an energy storage system can be comprised of batteries. I think that's one of those things that they're going to fix. We talked about it goes to the premises wiring system. An energy storage system can include inverters. They pretty much all do for the listed ones. There's other types of energy storage system too, besides batteries. So we have capacitors. Capacitors, they're not very good with storing lots of energy. So let's just even talk about like energy density, energy per volume. So that's like how big your battery is. So that's really important for your phone. So it fits in your small pocket. Energy per weight, which is more important for cars than volume. That's called specific energy. A lot of times when people say energy density, they mean specific energy. Anyway, capacitors have terrible specific energy. It takes a big space for a capacitor. Capacitor is like you have two plates. One of them's got all the electrons, and electrons repel each other. They want to go to that other plate. So what you have with capacitors, they don't put them in a car because it's not going to get you that far. But man, would it peel out because they have a lot of power. They can release everything all at once. But maybe someday somebody will invent the perfect capacitor that will go forever. And then there's flywheels, spinning things, another type of energy storage. It's kind of neat, but it's just not going to be lithium ion that soon. And then compressed air too, storing energy with compressing air like an old used fossil fuel cavern. It's like you pulled something out of there, blow some air into it. Maybe they could blow some hydrogen into it too. Another thing just mentioning while we're talking about hydrogen is hydrogen's round trip efficiency is somewhere around 35%. And so that's why it has trouble competing with lithium ion battery, which is somewhere around 95%. So just keep that. There's a flow battery. It takes up more space than a lithium ion battery. The big benefit of a lithium ion battery over the flow battery too is it takes up less space. So they use it for electric vehicles. It takes up less weight too in space. and they use it for electric vehicles. Electric vehicles get the mass production thing going. So the prices are dropping like crazy for lithium ion batteries. It's hard to compete with lithium ion batteries now just because of that. Even if your flow battery is the greatest thing in the world, you're not mass producing them like you are lithium ion batteries. And so lithium ion batteries are winning the race to be cheap. Because if you're doing a stationary energy storage system, it's not as crucial like as a car, like how big it is or how heavy it is. So we talked about like some of these listings, and the one that we want to look for an energy storage system is 9540, and they call that an umbrella standard. If we look at these energy storage systems, underneath that umbrella of 9540 for the energy storage system is the battery listing of 1973. I would just say, look for that 9540. You're probably not going to buy something that doesn't have that anyway. And if you do a lead acid battery, it's interesting that you can't even do that. You can't even find a 9540 system that works with energy storage. They get them listed together. So like, just say for instance, Solar Edge, they can only work with LG Chem because they got listed together that way. They could probably wire it right up with another LG Chem competitor's battery right now, but they need to go through the listing process to make that work. Let's see, the Powerwall 2, or that's just the Powerwall these days. There was a Powerwall 1, but they barely made any of them. That was a DC battery. That's because 9540 and 1973. The LG Chem is only going to be 1973. And then so you have to use it with an inverter that's done the 9540 with it. Those are a bunch of energy storage system, a bunch of Powerwalls. We can put more of them together on one system. So there's 10 Powerwalls, there's 10 inverters. So that guy's got some money. Huh? But what's kind of interesting is like they're over 10 kilowatt hours, but they're pretty close. It's almost like one car's worth, but those batteries probably cost more than a car. So it's kind of funny how it's cheaper to buy the whole car. So it'll be nice when we get EV to grid, and then we can compensate for that. And it's like, if my grid only goes down every once in a while and I have an electric vehicle that's got 100 kilowatt hours in it, I could just plug in and totally get through that blackout way better than having a power wall. And then if I run out bad enough, I can go find an EV charging station that's open and then bring that electricity home. Like, can you go to the store and get me some energy? So it'll be neat to see when that happens. Energy storage systems need a disconnecting means. Sometimes they're built right into it. And I always think that I hate these switches because O is the first letter of off and on. With these kind of switches, O is for off. I always have to even read it myself. I think maybe binary, ones and zeros. And so the one is on, the zero is off. Maybe that's the easiest way to do it. Ventilation is only needed really for certain kinds of lead acid batteries, the ones that can off gas. And so people would mistakenly think they need to ventilate a lithium battery, and you don't have to do that. This is another thing about the NEC that's just confusing, is it says energy storage system shall not exceed 100 volts. This is also for a dwelling. And so it just usually means 1 and 2 family dwelling. And then it says, but if you don't do maintenance on live parts, you can go up to 600 volts. You look at a lot of these energy storage systems, and it's just like what comes out of it. It's like alternating current is over 100 volts for everything. And the energy storage system is coming out alternating current. And so I don't know of an energy storage system. There's no listed energy storage system out there, you could say, that's even less than 100 volts, because a 9540 listed system, it's got AC on it, and you'd have to go all the way to Japan to find 100 volts AC. And they don't even use the NEC there. We got to change that. Then I could do more classes in Japan or do some class there. Or go there and tell them the way it is. I don't think they'd like that. Other things with energy storage system, we just got to follow the regular parts of the National Electrical Code. And so there's different things about working spaces around equipment. And 11026 is oftentimes used. And so this is for PV equipment and energy storage equipment and all different kinds of equipment. And what we have here is typically often for most jobs that you put something on the wall, 3-foot depth. So you got to be 36 inches away from it. So you don't put it in some narrow closet, 30-foot width, or at least width of the equipment, and 6.5 feet high, just like a regular basketball player. And that's just what a table looks like in the NEC. As far as sizing the circuits, wire sizing is the most difficult part of the NEC, I think. Almost nobody does it right. And if you meet the top 5 experts in the world and to ask them how to do it, they'll probably even disagree on it. In a couple of my books, my more advanced books, I have wire sizing chapters. Sometimes I'll go over people's work and about wire sizing and check it. They'll be like, I want you to check this guy. And I've never seen anybody ever do it exactly right. And so I turned it into a 12-step program. With batteries too, like you're working off grid and you need surge currents. So like you turn on a motor and it might use triple the current for a half a second just to get that motor kicking. And then it like, so let's say your motor uses like 1 kilowatt motor, but all of a sudden it's 3 kilowatts just to get it kicking, and then it goes back to 1 kilowatt. So off-grid inverters can handle those surges. Oftentimes you have to read the label and see what it can do. But when you size the wires, you don't do it based on the surges. You do it based on the continuous current. And continuous means like, it can handle that current for 3 hours, because you size a wire for heat and things take a while to heat up. And so that surge isn't going to cause it to get super hot. There's also something called a diversion charge controller. Let's say that you're off grid and it's a sunny day and you're not home and your battery's fully charged, or you're just slow charging your battery because it's called an absorption charge. You don't always give it all you got. So you got this extra power that you could just either throw away, or sometimes people will do a dump load, which they'll have something that just heats up, or they'll pump water with it, or they'll do something useful with it. That would be a diversion load. And some people even consider a diversion load being when you're connected to the grid and you start feeding power to the grid after your battery's full. And so there's special rules about diversion loads. Things is if the diversion load breaks, you got to have backup for that. So, if you don't burn up the house. Some things have diversion load controllers on them. And then for diversion loads too, there's certain rules where you have to oversize things by 150% just to be on the safe side, so you don't burn things up. And so now we're off to fuel cells. So fuel cells, what they need to do is they need to pump electrolyte. So it's sort of like a battery, and then to increase your battery capacity, you just get a bigger tank. Your tank's electrolyte. And then main type of technology they use is called vanadium redox. And they have like the different ionized types of vanadium. They pump it around and there's a membrane in between them. And it's a lot like a fuel cell. A flow battery is a lot like a fuel cell. So it even refers us in the NEC in Article 706. What you would do is even go to Article 692 fuel cells and use part of that article if you're doing a flow battery. So they're just like that was just a picture of a flow battery. It's got different tanks of things. You got tanks. You have to put the name of the chemical that's on there for that flow battery that's like a fuel cell. There's always going to be lots of signs for things. And containment, so you don't get a spill. Some of these things too, though, are like one type is a zinc bromine, energy production being really toxic. And this is like, it probably cures COVID. Zinc bromine, it's like got zinc in it. It's got, bromines, at least in Mountain Dew, keeps you going. So at least in pineapple, there's a lot of things that aren't. So, you look at solar modules, it's silicon, very non-toxic. There's just like lithium. A lot of these things in renewable energy industry aren't too toxic. And I notice a lot of people, though, they're like, solar modules are toxic because they cadmium. Well, there are solar modules that use cadmium, but it's like really small amount of the most toxic thing, probably a solar system, is driving the diesel truck to the job in the morning, or the secondhand smoke for the solar installers. And so what we have here is flow batteries has valves and pumps. It's like plumbing. They got to be careful of that. And we're looking at, there's just some different tanks for electrolytes, positive and negative electrolytes. And then other energy storage systems, like there's certain things, like if you were looking for things, they're like compressed air or flywheels. There's not a whole lot about that. So it just says follow the code. So you're going to hook wires to something and not blow things up. That's kind of what the code's about. Don't start a fire. And even like if you look before 1984, there's no NEC article for photovoltaic systems, but you still followed the code. You just didn't have a special article for it. And so you just do the same wiring methods they did for other stuff. There we go. We're moving along. And now we're looking at standalone systems. And this used to be in Article 690.10. And I always remember that it's easy to remember where it was because 690.10 is now in 710. So it's 710 and it says 710.15. Most of 710 is in 710.15. And it's mostly just like cut and paste. So they just cut and paste things. This is a friend of mine's house, but he passed away, but his daughter's my friend and she lives there now. And it's called an earthship. And the community I grew up in, there's no such thing as a building department. He's got all this recycled material. There's a 36 cell modules. So they're called 12 volt modules. They've been around for a long time. And what he did with this system is somebody gave him two more. And so when he got two more modules, he all of a sudden had to put different things in series that were dissimilar. So you're not supposed to put dissimilar modules in series unless somebody gives them to you for free and you live off grid. But because if you have things that are in series, the current flow is limited by the weakest link. These ones are a little bit less than those because these ones on the right are newer. So they're going to draw them down. I remember I told him, I was like, that's not, he's like, nuh-uh. He's like, it sure works great. And it looks really neat with this thing called a passive tracker, and it follows the sun because sunlight hits a canister and it heats it up and it makes it lighter and then it turns. It's kind of a neat system. But just also two neat things about this. He's got gallon jugs with rebar making his wall over there. He's got solar thermal and all that. These are Arco solar modules. So these are the first system I worked on. Was my dad got these in their Arco solar modules, and they got that antiquing look to it. It looks really nice. Monocrystalline silicon. I found somebody that was selling some, so I got 12 of these for, I think it was like, $300. And so I could give them to gifts to people in the solar industry, but they still work great. So it just goes to show you that just because somebody's got a contract for 30 years or a warranty for 30 years doesn't mean it's not going to last forever. I mean, the PV that they put on the Great Pyramids of Egypt 3,000 years ago still works. Crystal magic. That's what we stole that technology from the ancient aliens, if you watch the History Channel, right? The Solar Living Institute in Hopland, California. So they actually had an ASES chapter, but they went out of business during COVID. Shout out to them. There still is a guy, John Schaefer, started that, but he sold it and somebody else shut it down there. This is a picture of Peru, the Inca Trail. There's monocrystalline silicon, polycrystalline silicon. So I just had to show you that picture because I wanted this trip to be a tax deduction. So are we good? All right. But it was north facing solar. It was kind of interesting. And it's totally off grid. And so all you do with some of these off grid, these small off grid systems is you just have like a little charge controller. I carry one in my suitcase. It's in the car right now. I got a little charge controller. I got a little inverter or not an inverter. So you don't over and undercharge the battery, and you can charge your phone, charge a radio. They just have a minimal amount of electricity with that system. 710. Some of the things that they've done it a little bit differently. They're starting to transition from the word standalone to island. So they call it standalone mode, they call it island mode. So it's an island of electricity. And so that sounds good. I did a class for all the inspectors in Hawaii a few months ago. And that's why I left the palm trees up here, and we call it island mode, and it makes them happy. If we call it anti-islanding, if it's a grid tied. So anti-islanding means it can't become an island of power. So if the grid goes down, of course, you can't power the whole neighborhood, so it shuts off. And now what we have here is, this is just for a standalone system, a special rule that we've had in there for a long time. What happens a lot of times is people have a 120 volt inverter for off grid. And you go out there and you go to the electrical supply store, and they're not selling you 120 volt equipment. So you get 240 volt equipment, and you make line one and line two, you just bond them together. So they're at the same voltage. So then there's a problem, because it's possible that you could overload the neutral, because all of a sudden, instead of these two, line one to neutral and line two to neutral, opposing each other, and it's this really creative thing that we call split phase that we just have in the United States, where they oppose each other. And so the neutral only carries unbalanced currents. And so if you're balanced, like coming out of inverter, that neutral has 0 on it. So now if you're you got them both on the same, then they're not opposing each other. And so it's more current on the neutral. It's like double of whatever line one and line two is, or, you add line one and two together. And so there's this rule that says you can't use multi-wire branch circuits. You got to put a sticker that says that. And a multi-wire branch circuit, that's some people know it as Romex is one example of that, where you have black, a red, a white wire, and then a ground. So it's 3 plus a ground. You can't use that when you're going to do a 120 volt inverter, and you'd have to put that label there. Here is something that we have: energy storage system. Off-grid system, standalone system does not have to have energy storage. So here we go. We got a direct PV, and cows do like direct PV. The energy storage is not there. Just like the sun's out, it pumps water. There are some inverters, even like the SMA has an inverter that has a backup circuit that works without energy storage. So the sun's out and you flip a switch and you can power an outlet. So that's kind of a neat option that a lot of people even install the SMA inverters and they don't even hook that thing up. And I think it's just a neat little thing, but it does take a little bit extra to install it. So let's see. So we have direct current microgrids And that's just like you're connecting a whole bunch of things together on the DC side. And this is probably going to be brought over into Article 705 at the next time around the code. So here, just a little quick shout out to electric vehicles. And in the 2020 NEC, they changed it from charging to power transfer. And that's because we're going bi-directional. And it's just we saw Emery Levins talking about that too. That's going to be huge. We're putting all these electric vehicles on the grid, and then we can like use that electric vehicle energy. Instead of just being a load, we can be a source. And it's not like you're going to wake up in the morning, your battery's dead. You're going to be able to like program it and tell it, like don't go below this percentage or anything like that. And, you're going to have to give it permission to do that. But you could go away on vacation and come back and your car made you some money. The vehicle manufacturers complain. They're just say like, well, it's the warranty. Well, they should just warranty how many kilowatt hours you're going to cycle. It's like, I can drive it down the road and that's the warranty. So why not just like throw how many kilowatt hours you can cycle? And it's like, if I just have an electric vehicle and my power goes out for 2 days out of the year, that's just like taking a road trip, as far as it's not that big of a deal to just power it with your car. And so I think they're just trying to sell you power walls, like why they don't let your car do that. And so speaking of power walls and Teslas, so I did the first EV to grid. It voids the warranty. So I waited until I was getting my car serviced. And then I did it to the loaner car. And so I hooked up, they have a DC to DC converter with a high voltage battery. There's a 12 volt lead acid battery in the car. So you hook up the grid tie inverter from eBay and you plug it in the wall. And this is just a meter to see what it's doing. And then this goes and gets plugged into the wall. And so I was dumping out that 12 volt battery going into the wall at 70 watts. And then it turns on the big battery and then it starts draining the big battery. So and I've heard of some people that there's a lot of chat rooms out there. They're doing this with Nissan Leafs and other kinds of cars too, where they'll put a 12 volt standalone inverter there and be able to keep their refrigerator going when the power goes out. There's ways to hotwire it, but they probably might be able to figure out what you're doing with their such smart computers on wheels there that you have. That's the big future. That's really exciting, is going to be electric vehicle power transfer system. And that's going to be EV to grid. There's just a lot going on with that, Article 625. And we're just seeing tons of energy storage on wheels. This goes with energy storage and PV. So this is our transition in between here. And it is Article 705. If you're from Southern California, you got to remember that because you're on the freeway. And so we think of this as interconnections mostly. So like we talk about like how we're going to connect to the grid. We got currents coming from two different directions. So we've got the connecting to the grid would be like load side connections. You heard of that, the 120% rule maybe. And supply side connections, a lot of you have heard of that before. Now what we're looking at is there's something called a microgrid interconnect device. And let me just kind of skip ahead here. And so we got Article 702, and 702 is optional standby systems. If you call it an automatic transfer switch, or automatic transfer equipment, and then it says you have to back up the full load. So don't call it an automatic transfer switch, call it a microgrid interconnect device. Then you don't have to back up the full load. You got a house and you're just like the power goes out and I'm just going to back up, a couple of things, refrigerator. I'm not going to back up the air conditioner and the hot tub. And what you do is you just, you get a microgrid interconnect device, and then that will do the automatic transferring for you. Sometimes you have something like that's internal to the inverter. A lot of times that's like the multi-mode inverters. It's got two different outputs. One's for island mode and one's for anti-island mode. Grid tie and not grid, or off grid is island and grid connected is anti-island. And sometimes you have it as a separate unit. And that's what Tesla does. They call it a gateway. And so they have a separate unit that does the anti-islanding, and then it tells that inverter to go into standalone mode, to go into island mode or not. Then we have a microgrid system. And so this is something that has the ability to disconnect from the primary power source, which would be the grid. And this is also something that they're probably going to change in the NEC, because it kind of makes it sound like a microgrid has to be able to connect to the grid. But it doesn't, because you could live on a mountain and have a microgrid, and the primary power source is the grid. And so people are saying, well, the excuse is like, well, maybe when the grid comes here someday, I still have the ability to do that. Now what we're going to do is look at some of these interconnections. And this is like when we do a lot of NEC classes, we get kind of deep into this. They did change some things for supply side connections. The most noticeable thing that they changed when they went from 2017 to 2020 NEC is they just changed the numbering. So it went from 705.12a in the early version, of the NEC in the 2017 to 705.11. So it's got its own place there. And what a supply side connection is you're connecting between the meter and the main breaker, usually the main service disconnect, the first overcurrent protection device. So you're over there where things are not protected. You're over there where the utility is. You're adding your little insignificant amount of power to that giant, great nuclear power plant or whatever else is out there. So when you're out over on that side, it's not like you're going to be like adding extra power to your loads because your loads are already protected with the main breaker. When we do a load side connection, it's like, oh, we're adding extra power besides what that main breaker can supply. So it's kind of more of a big deal there. When we're doing a supply side connection, you can add, and let's say in the 2017 NEC, the sum of the overcurrent protection devices, that's breakers coming from the supply side connection, cannot exceed the rating of the service. So those are the wires that are coming, between the main breaker and the meter, or even, it can't be bigger on the other side of the main breaker too. In 2020, you can even put more. The sum of the power source continuous current shall not exceed the ampacity of service conductors. So before it was the overcurrent protection devices is what you were comparing the service to. Overcurrent protection devices are oversized for safety by at least 25%. And so here we're just saying the output power of the inverter can't exceed the service conductors. So that's like getting kind of close to the edge there. It's like, we've got a big supply there, but utilities get close to the edge. So why can't we? They'll actually put more current on a wire than the NEC says it can carry, but that's because the utility doesn't have to follow the NEC. They can do whatever they want, or they follow the National Electrical Safety Code. Some people say that the utility, what it uses for overcurrent protection is a lot of times they're using aluminum conductors. And so the aluminum will just melt. There you go. That's a real safe. I wouldn't want to be standing under that conductor while that happens. I hate getting aluminum showers. There's other things too, though. And it says, and other than those currents controlled by 705.13. This is a new important thing in the NEC that we're not really using yet, but we're going to start seeing it evolve. It might be the coolest thing that's coming out of the 2020 NEC. 705.13 is called power control systems. So that means that we can use electronics to control all these currents. And then we don't have to follow, as long as these electronics are making things safe and there's not going to be too much current, then we don't have to follow the load side connection rules and the supply side connection rules because we have electronics covering these power control systems, PCS. And so these things will just control the currents. And it kind of makes sense. Like if you think about it, if you have a PV inverter and a battery inverter, it's not like you're going to blast both of those full speed at the same time feeding the grid, because when the PV is going at full speed, you're charging the battery, you're not discharging the battery. So as long as we control those things together and we make sure that we're not blasting them both out to the grid at the same time, then things are going to be safer. And so that would have to do with power control systems. And then also throw in a bidirectional EV, which is kind of just an energy storage system, really. Here's just some for supply side connections. New rules too for 2020 is we have minimum wire size. So 6-gauge copper or 4-gauge aluminum. The wires can't be too small. That makes sense over there. And we need to comply with Article 230. That might change a little bit too, but we're going to ground it like a service for sure. An earlier version, supply side connections, it's like you could ground it like a service or not, just different interpretations of that. And here it's pretty plain and clear to ground it like a service. So bond neutral to ground separately. And that might change back to the other way where you could go either way. And then here's some other new things too, like for overcurrent protection with supply side connections. And another thing about supply side connections is oftentimes the slang term for that is line side tap. It's not really a tap, like you don't follow the tap rules. So the correct term is supply side connection, but like half the people out there say line side tap. So you'll hear that out there. Outside of a building, not as many extra rules, but inside of a building, the overcurrent protection device, 10 feet from the point of connection inside the building. If it's not a dwelling, so we're, commercial building, something like that, it would be 16.5 feet. The reason that's an odd number is because it's converted to meters. Or if you wanted to go further than 16.5 feet, you can put these things called cable limiters in there, which is sort of like a overcurrent protection, just only for short circuits, for like super high currents. Cable limiters. And then, because if like you got two wires that cross each other, you want it to open up the circuit, burn up these cable limiters before they burn some, the whole wire. And then you could go 71 feet. So I just thought 71, that's kind of a weird number. This is from the NEC handbook. So we're just showing how like you have multiple services on a building. So like 3 different apartments. And what they do here is they bond neutral to ground. So there's a white wire and a bare or green wire in 3 different places. That's just kind of how it's pretty much the best way to do it anyway, to do it for a supply side connection, because you're all on the supply side of overcurrent. There's no overcurrent protection device over here between you and whatever is coming from the utility. There could be something at the transformer, but it's not something that we consider. And so you do it differently. And grounding is one of those things too that everybody argues about. And I think that the reason they argue about it is there's just no perfect way to do grounding. You do it one way, there's one problem. You do another way, there's another problem. Currents travel through ground, and you put 2 electrodes and a lightning bolt comes here. The current might go through the wire faster than the ground, and you could get different voltages. And if you live in Florida and where there's a lot of lightning, you might install something a little bit different than if you lived in a place where they don't have much lightning. So there's just nothing perfect. And so inspectors like to talk about grounding, and people like to argue about grounding. Now let's jump over to load side connections. There is different ways of doing load side connections. And so this is not between the meter and the main breaker on your house. This would be between the main breaker, or main service disconnect, and the load side of it. So loads are all the light bulbs and all the things that go there. We call it, this is Article 712. And so it's always been 712, but 705.12a used to be supply side connections. And now they just took something out of B and they shifted it up to A. And then some of the numbering is a little bit different here. But I like looking at pictures. So we talk about connecting to a feeder, but what we have here is what's called a feeder. And so a feeder is going from the feeder breaker in the main service panel, or it could even just be one breaker going to the utility, but we're going to call that a feeder because there's overcurrent protection, and then it goes a long distance there, and then it's going to a sub panel. So let's call that the feeder. But we could also even kind of look at this as being the feeder. It's like, depends on the way you look at it. You have to look at these things from different angles. And these are things too that a lot of people don't understand and people argue with. And in fact, when they first came out with this rule, we did a video with this guy named Mike Holt and Bill Brooks. And they were arguing with the night before of how, which way was the right way. And and I think it took like a couple of years before people really started agreeing and changing their minds and coming to a consensus on how to do that correctly. So what you have here, you have the feeder breaker. And so this has got 100 amps to it. And we're protecting this conductor here so it doesn't have more than 100 amps going on it. And then all of a sudden somebody pops in an inverter and they're adding another 12.5 amps here. So what do? So there's not going to be any time where we're going to have extra currents going from that inverter. Like if we turned off this sub panel, still the most you get going that direction is 12.5 amps. So that's not a problem. But going this way, if the sub panel was like overloaded and power strips are going into power strips, we could potentially have 112.5 amps going on this conductor. And this is just for an example. Maybe it would be a 100 amp inverter, but just for this example, we're doing 12.5. So what we do here is there's a couple of different solutions how to deal with this. The first solution is if the conductor is big enough, you don't have to worry about it. So you could swap out the conductor, or maybe it's already big enough before you ever showed up there. And we don't use 12.5 amps in the calculation because when you're doing wire sizing, there's like going to be like overcorrections and things like that. And so we take 12.5 times 1.25, and that gives us 16. And so we just need to make sure that this conductor can carry 116 amps. And so that would be nice and easy. If that conductor can carry 116 amps, then we don't have to do anything. But if it can't, if it's a 100 amp wire right there, here's another solution. We put an overcurrent protection device here. And so we could put this one right here, and that works really nice. It's like that. But it's also kind of awkward to put, it's like this feeder was already there, and then I'm going to go stick this 100 amp overcurrent protection device. So that's kind of inconvenient. And sometimes a sub panel might already have a 100 amp breaker in it. So that would be the easiest way to do it. And so the question is can you do that? Because then what, is this still going to be protected the way that you want it to? And so what it comes down to now is the consensus has been, it took them, I think, about 3 years to decide how to interpret this, or, like a lot of people in the industry. You apply the tap rule, the solar tap rules that we're going to look at in a little bit. And so what it comes down to is that there's this thing called the 25-foot tap rule. And so if you're within 25 feet of this connection over to here, you can put that 100 amp breaker in the sub panel. But if it's greater than 25 foot, then if you had a really smart inspector giving you a hard time, they were not going to let you put it in the sub panel. But when you get down to this stuff, it gets really difficult. And then also under engineering supervision, you can do it all kinds of different ways. If you had a professional electrical engineer, you could do it a different way too. And that's actually there in the code. We have some different numbers, but same thing. So there's the feeder breaker, and then there's the inverter. And then if we're within 25 feet, so it says 24 feet, we can put it there in that position. This type of stuff here too that I was just showing you about tapping the feeder. I don't see a lot of people even doing this, but those are the rules out there. Here's all the bus bar ways, and this is where the world famous 120% rule is that everybody knows about. And one of the things that we even did in the last version of the PV and the NEC book is we even changed it to the 120% option, because too many people were thinking that, oh, you always have to do it this way. And it's just one of the options, one of the ways of doing things. So you don't always have to do that. We're going to look at all these different ways of doing things. Here's the engineering supervision. And so let's just look at pictures. Pictures are more fun, especially when you only have a couple hours to do a full-on NEC class. 100% rule. So this is not the 120% rule, but the reason is the 120% rule, we'll skip ahead, has to have this little sticker here that says, do not relocate this overcurrent device. The 120% rule is like, you have to be on the opposite end of the bus bar from your main breaker. You got to be on opposite ends. And that's because, so you don't overload that bus bar. So solar's feeding it from one side, the main breaker is feeding it from the other side. And so that's why we have the 120% rule like that. And so the 100% rule, you don't have to put it at the opposite side, but you're more restricted. If we had a 200 amp bus bar here, you say that panel board's rated for 200 amps, and we put on 125 amp main breaker, then I've got 75 amps to work with that I could put anywhere I want. So you could see that these have PV inverters right next to the main breaker. I like to call that the 100% rule. A lot of people call that 100% rule is the way to do that. And so it's not that hard to relocate things to the opposite end, but you might want to do that. A lot of times it's pretty common to have the bus bar rated for 25 amps more than the main breaker. So you might have a 125 amp bus bar, a 100 amp main breaker, a 225 amp bus bar, and a 200 amp main breaker. Then you could put a 25 amp solar breaker wherever you want. Or if you wanted to go more, you got to go to the opposite end of the bus bar. And then we're going to see here, if you exceed it by too much, then you can't even do the 120% rule. So let's just look at the 120% rule. And it used to be the 120% rule was based on the solar breaker size. And then I think it was in the 2014 NEC, they changed it to, instead of saying the solar breaker size, because sometimes people would put one microinverter, which is like about 1 amp, on a 20 amp breaker. And so all of a sudden you're dinged by 20 amps for using 1 amp. Now it's based on 125% of inverter current, which is how you size overcurrent protection devices. We're going to say that if we put things at the opposite ends of the bus bar, we'll say that the main breaker plus 125% of the inverter current cannot exceed 120% of the bus bar rating. So we take the bus bar. So let's just do like a calculation. Bus bar, 100 amps, 100 times 1.2, 120 amps. You got 120 amp allowance. And let's say we had a 100 amp main breaker. So that leaves us with 20 amps for the solar. And that 20 amps for the solar, or it could be energy storage, is that 20 amps is 125% of inverter current. So a 16 amp inverter times 1.25 is 20 amps. So the most we could have is a 16 amp inverter. That's a pretty common thing. 16 amp inverters are more popular. 16 amp inverter is a 3.8 kilowatt inverter, and a 3.8 kilowatt inverter is way more popular than a 4 kilowatt inverter because of that, because they make it to fit on a 20 amp breaker. And that's for 240 volts too. So when I say 3.8 kilowatts, that would be 240 times 16 amps is 3840 watts, 3.8 kilowatts. And then it needs to have that sticker there at the opposite end of the bus bar. And here it is too. One thing that was kind of confusing, I think it was worded wrong in the NEC, was they almost made it sound like it had to be one breaker. let's do the math again. So let's say that we have 200 amp bus bar times 1.2 is 240. Subtract off 200 amps. We got 40 left over. We could do the same math that we were doing before. And so that would be two 16 amp inverters, which would be two 20 amp breakers. And so there's two 20 amp breakers. And we could put two 20 amp breakers down there. It doesn't have to be like one 40 amp breaker and then combine two together with a sub panel, which some people think that it should be. And it is up to the inspector to decide how to interpret the code, but it was intended. You didn't have to have just one breaker feeding these inverters. A lot of times it is one breaker because you'll have somebody else owning the PV system and they need to monitor it very carefully, because the owner of the solar system, that could be somebody like Tesla or Sunrun, somebody like that, that the owner of that solar system is going to carefully monitor that. And so they're going to do it with, put it all the solar on a sub panel and then just feed it to one breaker. You'll oftentimes see stuff like that. Okay, there's how to do that calculation really quick for the 120% rule. And a lot of people too, especially even like solar salespeople, they just have this in their head. They don't even do the calculation. This comes from the solar ABCs, expedited permit process. So somebody's done all the math for you. What's the biggest inverter you could put on your house with all these using the 120% rule? So there you go. And once again, everybody's going to get this presentation when we're done. This one is called the sum rule. I call it the sum rule, but some people call it the solar plus the load breaker rule. And this one, what was put here before is we were penalized for the 120% rule a lot of times. And what that was is if we were just combining inverters. So let's say I had a 100 amp sub panel, I should be able to put 100 amps of inverters there and combine them together, because I'm never going to send more than 100 amps back. And you couldn't do that with the 120% rule. If you had that situation, you would have been limited to 60 amp of inverters with the 60 amp main breaker, because 60 and 60 is 120. And so I say 60 amps of inverters, I mean 60 amp of inverter breakers would be the maximum. So 125% of inverter current. So then with this new sum rules, let's just read the label. This equipment fed by multiple sources, total rating of all overcurrent protection devices, excluding the main supply overcurrent device, shall not exceed the ampacity of the bus bar. You ignore the breaker protecting the bus bar, and we're just protecting this bus bar in reverse, and we're kind of overcompensating. And so you just add up all the breakers, solar and loads, you put them wherever you want, and they just can't exceed the rating of the bus bar. And so this is something that's actually being used kind of a lot. We're going to even look at what they call the Hawaiian tie-in. And here it is again, just the same thing. You just add up all the breakers. I think you should be able to just throw away the main breaker. This is one that was kind of thrown in as an amendment to the NEC, to the 2014 NEC. And then the 2017 NEC was kind of unfair because this is the 120% rule for center-fed bus bars. And so a lot of times the further west you go, the more oftentimes you have a center-fed bus bar. You got a main breaker in the middle, and then you can put solar on different sides of that bus bar. So the 2017 NEC said you could pick one side or the other, but not both. 2020 NEC, they got rid of not both. So you can put, like, if I had the 120% rule and I had a 40 amp allowance, I could put a 20 on each side. If I'm doing the 120% rule, I still need that do not relocate sign. There's another thing that's under engineering supervision with multi-ampacity bus bars. You can do whatever the engineer says, and then engineer will have insurance in case they burn your house down, right? Maybe we could do the 200% rule. We can, as long as the engineer says it's safe and they do some calculations. There's nothing really wrong with the 200% rule. And I'm just saying, instead of the 1.2 multiplier, if you had a 100 amp bus bar and it was fed by 100 at the top and 100 at the bottom, and you had 200 amps of loads in the middle, you'd have 0 amps and you'd have 100 amps on each side. So you'd never have 200 amps running through that bus bar all at one place. There's an argument for the 200% rule, but there's an argument against it that still you just have too much heat on that thing because it could generate heat. So under engineering supervision, you can do things. And then there's also something called feed through lugs. So sometimes that you have a bus bar that you can screw conductors onto the bottom of, and maybe it's already at your house. The way I just explain it is you just treat that as an extension of the bus bar. If you got these Bolton conductors on the bottom of that bus bar, and actually I saw that here last year in Colorado. It was the first place that I went after being locked down for a while. A company hired me to come out and do some jobs. And I was like, wow, you guys are eating at restaurants? And it was like, because they were eating at restaurants. So here we've got, I talked about this before, 705.13, and this is the one that's called power control systems. That could be a big change, but we're going to need to have some special equipment that deal with this. And so as long as you control things and control the currents, and you'll have current transducers, and this is going to be a big thing, and they're starting to use it, then as long as you have this, you don't need to even follow the load side connection rules or the supply side connection rules, because you can just control these with smart electronics, silicon chips in the brains of these systems. And you could limit the currents on all these conductors. So that's just a real neat thing that we have. There will be settings and programming going on, and we should only be programmed by qualified people. So you're not going to have the homeowner going like, I'm going to tweak this, make it work better. Sometimes you combine it. So you might not be controlling everything. And so the thing that you're not controlled might still have to follow the 120% rule. But you could do for more than the 120% rule. And we kind of already talked about that. It's power control system. Just look at some pictures. So this one is the 120% rule that I talked about. 16 amps times 240 volts for your house is 3840 watts. And that goes on a 20 amp breaker, because 16 amps times 1.25 for safety is 20 amps. And they go on opposite sides. So there we go. This is a supply side connection. We're going between the meter and the main breaker. And you can put almost as big as you want there. There's very rare cases where you would want to put more than the service entrance conductors can handle. Maybe you have a Bitcoin mining operation or whatever they do with lights here in Colorado that you guys are famous for. These indoor light bulbs, indoor lighting systems. Some of the things that people are doing too is, and we did this at my mom's house. She had a 100 amp panel board. Everything was full and I wanted to add a bunch more solar. We put in a 200 amp panel board, but we left a 100 amp breaker. And so after doing the 120% rule there, you've got all kinds of room for everything. That's really nice for adding solar and energy storage and bidirectional electric cars. So you'll see a lot of people doing that. And then some people call this one the Hawaiian tie-in. You've come up to a house and maybe it's like an all-in-one meter main where even sometimes the meter is built into the panel board and it's rated for 100 amps. And you want to do this thing, you want to add a 200 amp panel board, but it's like, well, shoot, that's going to be way, what am I going to do? Pull out the meter and tear the wall down. It's just going to be very complicated. And you want to be able to power all your loads with AC coupling and do all this great stuff. And so what people are doing is they're just kind of in a way bypassing this main service panel. So they have a 100 amp breaker here and a 100 amp breaker there. And so that's what one I called the sum rule. So just like, you can't add any more breakers. You got to put a label there. It says the sum of all the breakers does not exceed the rating of the bus bar. And then you go over here and you put a 200 amp bus. Heck, why not a 400 amp bus? Put a big old bus bar and it's fed by a 100 amp breaker. And so then you have all the benefits of this right here. So some people are calling that the Hawaiian tie-in. They do that a lot in Hawaii because it's famous for having 100 amp bus bars and lots of solar and lots of energy storage, and for having these all-in-one meter mains on the outside of the house. It just makes it easier so you don't have to, very expensive to start replacing all-in-one meter mains. These combinations where you have the further west you go, the more often you have it. I think they have it around here. So, but you got a meter and the main breaker and the panel board all in the same enclosure. And you're just like, oh, I'm stuck. Oh, maybe I'll just put a 100 amp breaker there and then put in a 200 amp panel board right next to it. And then I could do whatever I want. You get like all kinds of fun stuff. So backup power, we're going to have like lots of good reasons to have backup power everywhere, everything from preppers to just all electric lifestyle. This is kind of one way of doing it that's been around for a while. Multi-mode inverter. So this inverter has an output that's backed up. Let's say we're running on batteries. This multi-mode inverter can back up this sub panel, but this one would anti-island. So this inverter has two modes. It has island mode. This one it has the ability to do island mode and anti-island mode, disconnect from the grid. So the grid goes down and all these loads still work. So that's just a way that people have been doing it for a long time. We got pretty much the same thing. And so this is power control systems. So, and we also have energy management system. Could be like the same computer. We've got a microgrid interconnect device here, checking the current here. Here in Hawaii, you're not allowed to feed the grid. There's already too much solar feeding the grid. It's a small grid. So you have a current transformer or current transducer, a CT, they call it. You're monitoring right by the meter just to make sure that no electricity goes backwards. When it starts to get close to going backwards, then you start charging the battery or cutting things off and turning on different loads. And they have like all kinds of neat stuff. You pump water, you could heat your swimming pool, your hot tub, cool off your freezer extra cold, charge your electric vehicles. This kind of system that we have right here is the future with all this stuff. You know, we got PV, energy storage, another PV system you installed later. PV went down in price. You put it on the north roof. And then you have 2 different electric cars, and they're starting to get bidirectional. So you can control all this stuff. And so this is where it's going to be probably a lot of jobs, because it's going to take a lot of brains to figure out how to control and program all these things. That would be pretty neat. And then we have backup power, microgrid. So this is whole house backup. So that last one was backing up part of the house. And then this one backing up the whole house. That's a big question. Some people are, you know, don't back up the whole house. What happens is everything's on and the air conditioner's on and power goes out in the middle of the night and you wake up to a dead battery, you know. But you can have smart electronics that'll compensate for that. Or you can argue that either way. Okay, so now we're off to 690 solar photovoltaic systems. And so it starts off with some pictures. Just notice is in the 2020 NEC, they got rid of the word solar panel. So that was always, you know, complicated. You're going, it's a solar module, not a solar panel. And you're like, you're weird. You know, even the president calls it a solar panel, you know. So now we could say solar panel and not contradict the NEC at least. Yeah. So we got rid of it. Electronic power converter. I thought this is kind of funny how the changing some names. We got island mode. Now we have electronic power converter, and look at the acronym for that, EPC. So we know, like with solar, they're always talking about construction. EPC is like the guy that builds the system. So like there's somebody, developers and all that kind of stuff. And so this week I was working with Carpenters Union, and they're like all about EPC work. They're not going to be like the one developing the grid, doing all that scouting and all that. They're going to be putting it together. They want to build it. And so that's engineering, procurement, construction, EPC contractors. You know, it's like you go to China and everybody's talking in Chinese, and then you hear EPC. And you're like, oh, wow. Then you hear a swear word, but then everything else is in Chinese. And so now it means inverter or electronic equipment, DC to DC converter, charge controller. Could be EPC. So kind of funny. Electronic power converter. What they did that was a big change in the 2017 NEC is they changed the way they talked about grounding. And so in the 2014 NEC and earlier, we always talked about grounded and ungrounded inverters. They changed it. And so now the ones that we call grounded and ungrounded, like we don't really even use the kind, except for utility scale systems, that we used to call grounded, that were fuse grounded, that were not solidly grounded. And now they're not even called grounded. They're called functionally grounded. And so they kind of figured out the ones that we used to call grounded were only functionally grounded. And the ones that we used to call ungrounded really were a little bit grounded. So they are functionally grounded because the inverters that we use, the transformerless inverters, formerly known as ungrounded inverters, almost everything you use, unless you're doing big utility scale system, is like that. And so if you measure the voltage between ground and negative or ground and positive, it's not floating around there. It's solid. It's referenced to ground. So it is functionally grounded. So anyway, so we call them functionally grounded, and we have the same rules for both kinds of systems. And if you have an old, formerly known as grounded inverter, you can replace it with a functionally grounded inverter, and you don't have to change the wire types, and you don't have to change the fusing, because you only have to put fusing in one polarity. You could use USE2 wire for all the inverters now. And the one thing that's a little bit different is you're supposed to open up the circuits on positive and negative for the old inverters. So the DC disconnect maybe has to be rewired a little bit, but a lot of times the DC disconnect will just be built in to the inverter anyway. Even if you did it wrong, the newer inverters, you know, we used to call transformerless, are so much more safer anyway that whatever you did, if you put the newer inverter, it's just a lot safer. They're so much more sensitive at finding ground faults. DC to DC converters, also known as optimizers. And they moved some of these things from Article 690 to Article 100 definitions. So that means you're getting big time. If you're getting to Article 100, that's mainstream, and it's like tucked away in some 690, something like that. Inverter generating capacity, that's the AC output of an inverter. So if you're over 100 kilowatts, you get benefits for PV systems that under engineering supervision, and you could use different values for current and voltage. And if you're over 5 megawatts for a ground mount, you can use Article 691. So that's like, you know, utility scale and all that. Interactive just means it interacts with the primary power source, the grid, so it could feed the grid. When you put DC to DC converters together, those are also known as optimizers, like SolarEdge or Tigo. That's not called a PV source circuit anymore. It's called a DC to DC converter source circuit. And then if you parallel them together, you have a DC to DC converter output circuit. Typical system, you get a little cloud over this solar cell here, and it's taking out 10% of the whole thing. Really, if you were shading one solar cell, it would take out 1/3 of one module and then all the rest. So these numbers aren't exactly correct. You could probably argue some situation where maybe it would be correct, but you see people are saying module level power electronics. If you're trying to sell something, sure, you're going to like try to make yours sound better than maybe, or the other guy sound worse than it really is. We have DC to DC converters there, and then they're connected together in series. And there's a PV source circuit. It's just one module. And so that's just one module connected to that DC to DC converter. DC to DC converter is like a transformer, but it's for DC. Transformers only work for AC. So here we have 690.7. That's for voltage in the NEC. Here's the speed limit or the voltage limit. 600 volts for 1 and 2 family dwellings, 1,000 volts for other dwellings, and you could put a 1,500 volt inverter in your backyard. But usually, I don't know anybody has, but for utility scale, it's almost always going to be 1,500 volts. And that's your maximum system voltage. So like you put all your PV modules together in series and you do the calculations for the coldest day of the year and when it's turned off, and you can't go over 1,500 volts. And nobody does bipolar anymore these days, but there's something called a bipolar system. And you could really go up to 3,000 volts with a bipolar. You could double that. I just thought this was a funny picture. And at the big NEC solar show in China, where Dave Renee, who you might have seen here, he usually gives a big talk there. And so they put little cooling fins on the back sheet of the module that cools it off. And it's just like, yeah, you're going to spend more than the module costs doing this, trying to cool it off to try to get a couple % extra out of it. But it's kind of funny. It gets you to go to the booth. So there's different ways of calculating what's your highest voltage. It's voltage based on temperature. So first way is the way people mostly do it is they calculate it based on math, and they use coefficients. There's another way of doing it with this table. If you went down to 10 below zero, you get a 14% increase. So you multiply times 1.14, and this is Celsius, where it's got Fahrenheit over here too. And then if you're doing something over 100 kilowatts AC output, you can do it under engineering supervision, and then your voltage can go up even higher under engineering supervision. And they tell you to maybe use an electrical engineer, because sunlight hits the PV module and the sun heats it up. And so that's kind of what they're looking at. And you can even put more in series under engineering supervision. Okay, and then for your DC to DC converters, the voltage there is you figure out how many you can put in series. I mean, you just read the instructions. It's electronic equipment. It'll tell you in the instructions what it'll do. Here's a DC to DC converter, the most popular type of system that you'll see on a building these days in the United States because of rapid shutdown requirements. So there's a PV module. That's called a PV source circuit before the PV module goes to the DC to DC converter. And then coming out of the DC to DC converter, it's called a DC to DC converter source circuit. So yep, SolarEdge, you got it wrong. They called it a DC output circuit. That is totally wrong. They failed. So just be careful of that. This is just kind of funny that in 1950s, the electricians would test voltage with their fingers. So they could be like, oh, I could tell the difference between 240 and 208. And they would do that with just their right hand, and the whole circuit would come through their fingers. They wouldn't do it through their heart with the two different fingers. Maybe that's why none of them are around anymore, but they used to do it that way and tell you to do it that way. And even for lower voltage circuits, like communication circuits, they could do it with their tongue and they would come up with a taste like a 9-volt battery. But now if you do something like that, you're supposed to go get signed off by a doctor before you go back to work. Most electricians will just they're like, oh, I just got it again. I got hit again, But be careful, electricity, it can kill you. Something to be careful of. This was just something that I saw it's the biggest solar show in the world called NEC. I saw these weird shaped solar cells. So it just made me think, so the bigger the solar cell, the more light it captures, the more electrons it knocks loose, the higher the current. So we're going to talk about current, circuit sizing and current. And that takes us to wire sizing. Like I said, it's like the most complicated part of the NEC is wire sizing. All these different ways of figuring out. So PV is wild and it's like a crystal in the sun. So PV is just weird. Like most electronic equipment, it's controlled. And so you read the label and it says, oh, this is how high the current will get. This is how high the voltages get. With PV, it's like, well, What's the current going to be? Well, we're in Denver, so it's high altitude. There's not much air. So the current might get higher. Oh, what's the temperature? That's going to determine the voltage. So it always can get higher than what it says on the label. Most things aren't like that. For current, we're very conservative, and we take the short circuit current, which hopefully you never have a short. That's just like shorting out. And we multiply it by 1.25 to get our current that we work with. And then when we get our current, that's the current we work with. And then we multiply it by another 1.25 that we do for everything else, because it's something that goes for 3 hours or more. It's called continuous current. There's these two different 1.25s for a PV source circuit that you end up using. And then if it's hot, so you're in the sunlight, then you might have other correction factors. So it just gets kind of complicated with your PV source circuits. One of those things too, if it's 100 kilowatts or greater and you got an engineer to supervise it, you can actually use 70% of what you were going to use. So it's like I give it this 1.25, but then I can shrink it down again. So there it is, short circuit current times 1.25. And then you bring it back down 70% of that. So really it's short circuit current times 0.875 is like the least amount of current you could call it. Sometimes too, they could be like, do you really want to use the smallest possible wire that you can? Because you'll have so much voltage drop. But as PV is getting cheaper and cheaper, and pretty soon the way it's going down, I mean, it'll be free. When PV gets free, then we just worry about our wire costs. And then maybe we will start using like really super small wires. I mean, it's like a lot of times I've even done calculations for wire sizing where I could have used a 14 gauge wire, which like mostly people use 10 gauge wires, but you do the calculation, it's like sometimes it could have been a 14. Here's another thing that's new and a big change in the NEC for 690 is before we were always calculating our wire size for our PV source circuits based on the PV. But what we're doing now is we are oversizing our PV array. They call it clipping. So let's say that I had 2 megawatts of PV on a 1 megawatt inverter. And it's like, that's an extreme example, but let's say I did that. Well, it's never going to take in more than a megawatt or maybe a little bit more just for inverter inefficiency. Let's just say it's never going to take in more than a megawatt. So why do I have to size my wires for 2 megawatts? We're going to size it based on the input. And if we look at a battery inverter, that's kind of similar. So we got a battery connected to an inverter. Short circuit current of a battery is like tens of thousands of amps until the thing explodes. But we don't size that wire based on the battery current. What's the maximum current the battery can give out? We size that battery to an inverter. We size that based on what's the most current the inverter can take. What's the most current that inverter can take? Now we could do that with PV inverters. There's just a different way of sizing the wire for the input of a PV inverter, and it's based on the maximum amount of current the PV inverter can take, as long as you have an overcurrent protection device there too. That's another thing too that's a little bit different. It's a different way of doing it instead of basing it based on the PV. With DC to DC converters, just like with the voltage, it's going to be based on what the instructions say. So just say, for instance, Solar Edge, you want to read their instructions because they can have new stuff coming out and different ways of doing things, but 15 amps per circuit. And so this was the new thing that I just told you about. So we just talked about that. We can base the current based on the input of the inverter instead of the output of the PV. That's kind of a big deal. Here's just a little bit about wire sizing. I mentioned I turned it into a 12-step process, but you've got your maximum circuit current. That's for the PV, that's short circuit current times 1.25. For everything else, that maximum circuit current is just like the label on the inverter, what it says. And then you do some stuff to here, you do some stuff here, you compare the two different ways of doing it, and then you check it with this thing and you check it with that. There's a whole bunch of different checks. And I made it into 12 different steps how to do that. There's these different adjustment factors that are in those steps, and that has to do with heat. There's too much heat on a wire. You need a bigger wire or better insulation around that wire. Some things that cause heat is putting too many conductors in a small pipe. If I put 10 wires in there, it's like a 3-dog night. Those 3 dogs, that's what keeps you warm when you live in Alaska. It's 3 dogs. So you put more than 3 wires, more than 3 conductors in a wire, I guess that'd be a 4-dog night. Then what would happen is you would create too much heat in there. And then just high ambient temperatures too. There's another one that they got rid of, is it used to be you'd have to derate for how high you were over a rooftop. And they got rid of that after the 2017 NEC came out. We're talking about DC arcs. So that's a DC arc. Our inverters will see the signal of that arc, and then they'll turn off. You can see like DC arcs can catch fire. So if there's an arc, an inverter will turn off the circuit. Our inverters have to have DC arc fault protection, but you can also train animals to do this too. So like not everything is done with electronics, this is if you live in a cabin. What happened was there was a system, they installed it wrong, and there was too many leaves under there because the rail was installed too low, and then bad things happen. I know there's animal lovers here. I better just change that picture, sorry. For big PV systems, speaking of DC arcs, Article 691 covers large utility scale PV systems, and that's for 5 megawatts AC and over. And then you can avoid a lot of rules. The reason for this is you're pretty much a utility, even though you're not. And so like coal plants aren't in the NEC, natural gas plants aren't in the NEC, nuclear power plants aren't in the NEC. So why does a utility scale 5 megawatt solar farm have to be in the NEC? We just loosened the rules so we can be more equivalent to them. And so things will be under engineering supervision and you have less rules. And what you follow typically when you're a utility is not the NEC, but the NESC. That's the National Electrical Safety Code. And it's behind a fence and only qualified people are there. And even if you throw a Frisbee over that fence, you can't get into it, like on your roof. So rapid shutdown, 690.12, it's always something to talk about that people like to get excited about too. And there's 3 ways to comply with rapid shutdown. And traditionally, most everybody does number 2, module level rapid shutdown. 2 modules in series is over 80 volts and 1 module is over 40 volts almost all the time. Rapid shutdown has to do module level, 80 volts in 30 seconds within the array. There's 2 different ways of doing it though. If you had a system that didn't have metal parts, like no rails and frames, so maybe building integrated PV, then you don't have to do module level shutdown. And then there's this new listing 3741 that just came out. We don't see anybody doing this yet, but they're working on it. I heard Tesla is doing it. It's possible to have 3 in series because they tested like a wet firefighter with 3 modules in series and they were still okay. I mean, that's what the firefighter told me that was working on this. They changed some numbering here, but it's pretty much all the same. So keep your eyes out for this 3741 listed equipment. We'll see if when more of that's going to start coming out. And then that might make systems a little bit easier to maintain because module level shutdown has a lot of pieces of equipment over the next 20 years you might be replacing. And then when you're outside of the array, you actually out within 1 foot of the array, you got to get down instead of 80 volts, you got to get down below 30 volts in 30 seconds. That's 30 volts in 30 seconds. That's rapid shutdown. This is the new standard, just came out, 3741 that we were looking for. Sometimes you'll see 2 modules in series. That doesn't comply unless it's 3741 or one of those exception ways. That's not module level shutdown if you have 2 modules in series. So just beware of that. This is the sign that you put with something that has rapid shutdown. So that means it's safe inside the array. If you know firefighters, you can educate them on this and tell them that if they see that yellow sign, that they can go up there and they're not going to get shocked inside the array. Really hard to get shocked with a single module. If you have different styles of rapid shutdown, like you put different things on the building at different times, you'd have to put a map that shows the different styles that you have up there. And then the firefighters will get really confused. There's something that I haven't seen anybody use yet, but we have new things in the NEC that they put here that you can use 105 and 125 degree wires. And so there's temperature correction factors for these super hot wires. You could they work in boiling water. Boiling water would actually cool them off because boiling water doesn't get hotter than 100 degrees. So think of that, cooling something off with boiling water. Here's just these ampacities of these wires. And we'll see if people start using that. That would just mean you could use a really skinny wire, which I don't see anybody really using that. There's special rules for marking things. So circuits need to be marked with these PV systems so you don't get mixed up in one side of the conduit and the other. Another thing that was new, we've always used USE2 wire, and that's like that UV rated wire that's underneath the PV arrays. It's really common. You could also use PV wire, but in 2020 NEC, it has to be dual listed also as RHW-2. But if you went shopping, you could find out that all that USE2 wire you've been installing is already RHW2 listed. It'd be really hard to find USE2 wire that wasn't RHW2 listed, but that's just another rule that they put in there that probably doesn't make a difference because it already is anyway most of the time. And then another thing is that's kind of a drag for some people is the wires underneath the arrays, they have to be secured every 24 inches. And so the width of a solar module is like 38, 39 inches. You can't just have a conductor, even on your ground mount, that's going, more than 24 inches, makes things a little bit more difficult because it used to be 4.5 feet. Yeah, we're going from 4.5 feet to 24 inches. So we'll see, there might be some feedback on that, and they might change it back after a while. USE2 by itself can't go indoors, like in conduit or something, but RHW2 can. It's more expensive though, so you're probably not going to use that wire indoors anyway. Small changes too with this sticker every 10 feet on your circuits and at junction boxes and things. Now you can put less words. It doesn't have to say warning on it, and it doesn't have to be reflective. I think this probably has to do with people are just more used to solar, and the rapid shutdown makes it safer. And so this is a little bit less severe. It doesn't have to be a reflective label, and it doesn't have to say warning. And this also too is only for DC. Some inspectors used to make people put it on their microinverter circuits. Remember that? I always thought this was confusing. Flexible cords and cables. And so you're going to have fine stranded cables, which gets kind of confusing because this is only for tracking arrays. But when you first read this, you're like, do I have to have this many strands for my PV system? Only for a tracker. I wouldn't be surprised if half the PV in the country is put in with trackers, but it's these big utility scale systems. And so if that wire is bending, at least the wire that is bending, needs to be able to bend 365 a year. So you need to have a flexible wire, and it tells you what are the minimum amount of strands that you have there. So we talked about these inverters that were ungrounded and grounded. And so ungrounded inverters, transformerless inverters, that was an old NEC term. Now we just can call that non-isolated. Is a correct term for that, or just call it an inverter, because almost every inverter is that way anyway. And these are the different configurations that we have. One functionally grounded conductor, that would have been what we used to call grounded, fuse grounded. Not isolated, number 3, that's mostly what we're using. And let's see, just for grounding, you size your overcurrent protection, your equipment grounding conductor based on the overcurrent protection device size. I always thought this is kind of interesting. And there's all these arguments that they have about, like, can you put a ground rod here and a ground rod here and then have it hooked up through the array to the other ground rod? And there's like always been a big controversy and lots of fights based on that. 690.47, they talk about that oftentimes. And so what that's about is, like, the electricity, there's more resistance in earth. So if there's a lightning bolt in earth, there's less resistance going through the wire, and you can get all these different voltages. So if you're in a place with a lot of lightning, you can run into trouble, and you want to have all your electrode systems connected together in one place. There's something called step voltage. I just think it's kind of interesting. And so if there's a high voltage line or something that falls, if you took a big enough step, there might be different voltage in different place. And if there's a different voltage in a different place, the current might go through your body, and that kind of hurts. So just be careful of that. If there's a lightning bolt, if lightning comes, stand on one foot. That's all we're trying to say. And be careful of putting ground rods that are not bonded to each other before they connect to you. You don't connect ground rods together through an electrical system. Ideally, according to different theories, there's different ways of doing that. Now let's talk about some signage here. I'm going to just go to this page. So if we went down to the 2017 NEC, you have to have your maximum voltage and your maximum current. 2020 NEC, you only have to have your maximum system voltage. This is for like the DC disconnect. It's oftentimes it's just like on the inverter. So there's less stuff. And if you went to the 2014 NEC, you had to have your operating current, your operating voltage, your maximum voltage, and your maximum current. This requirement is actually getting to be less stickers. A lot of people make fun of, like, there's a sticker quota that you have for all these things. Like, did you meet your sticker quota? Less stickers. And then we did kind of talk a little bit about 691 large scale PV. So that's for 5 megawatts and larger, and it's never going to supply loads. It's only supply the utility. It's not like you're going to power your Amazon warehouse with this. You're powering the utility. And there's a lot of references to the National Electrical Safety Code. Things will be done under engineered design. And these are some of the things that you'll often differ from Article 690. So you can have different voltage calculations, even different current calculations, different PV equipment disconnects, so less disconnects. You have educated people in there, just have regular people walking around. You can get rid of your arc fault protection, which can save a lot of money. And also there's requirements for grounding of fences. So you got that there. Here's just some different things that they changed a little bit in the NEC that's kind of insignificant, but it's kind of confusing. Let's just show you. And so they changed 31015 B2A. That's ambient temperature correction factors. And so if I had a 90 C rated wire, temperature degrees Celsius was 35, then I'm going to have a 0.960 rating factor. So I'm going to only be able to carry 96% of the current. That's how you use this table right here. And this has to do this 90C is rated for the insulation. That's how the insulation is rated. And then this is the outdoor temperature. There's 30, and there's 30 is 86, 40 is 104, and then 50 is 122. So just kind of give you some examples there, but that's how you use that table. But they changed it just to make it more difficult from 310.15B2A to 310.15B1. That's all that's different. And they changed 310.15B3A. That's derating if I had 4 current carrying conductors because of a 4-dog night. Then I can only carry 80% of the current. So we're derating that wire by a 0.8. And they changed that to 310.15C1. Then this one is even more crazy because it used to be called 310.16. Then for a few code cycles, they called it 310.15B16. And now they've changed it back to 310.16. So at least it's easier to remember because that's what it used to be called. And this is probably the most widely used page in the NEC book. And so if I had a number 10 wire and I had an insulation around that wire is 90 degrees C, so that means that insulation could heat up to 90, then that means I could put 40 amps through it before it heated up too much where it would like wreck that insulation in theory. Usually it can carry a lot more current than these tables say. There's a lot of safety factors written in there. And so this is a very common book to figure out how big a wire should be. And then we've got 310.15B17, which is now 310.17. And that last one was for wires that were not hanging in free air, like not single conductor cables. But with PV, sometimes we have single conductor cables in free air, like behind the PV array. And those single cable conductors in free air, they get cooled off by the air as the air blows by it. Perfect timing for credit for this course. I'd just say like solarsean.com at the end. There's my email address. I can leave that up there. There's also just meetings for the 2026 NEC and 2023 in Golden. So let's go back. I'll meet you there. There's some of my books. This is probably just a good page to leave it on as we're finishing up because it's got my different contact information and stuff there. And so you have my email address and you have my website. Send me an email. Thanks for coming to ASES and coming to this presentation. ASES is great.
Thanks for listening to Sean White's Solar and Energy Storage Podcast. To find out more, like everything you want to know, and make the best investment that you possibly can into yourself, get educated and go to Solar, SEAN, that's SolarSean.com.